Take a look at this figure. It shows the stress-strain response for 5 different alloys. Simple question: which of these alloys exceed 100 megapascals? At first glance, you might say the purple alloy does, and maybe the green one as well. But now ask yourself, which alloys are these exactly? Given this color selection, it's actually pretty hard to tell which color corresponds to which alloy. Now look at the same data again. Nothing changed except the colors and markers. In this version, it's immediately clear. The green alloy and the pink alloy do not exceed 100 megapascals. This is the impact of proper color selection. The data is the same, but the information you extract is completely different. Unfortunately, suboptimal color choices, like the first example, are very typical in scientific literature. You can find them everywhere, confusing readers through ambiguous color choices and demanding unnecessary effort to extract meaningful information. Therefore, my goal in this video is to show you a scientific way to select colors such that your figures communicate data with clarity and impact. First, we'll discuss the 3 purposes of color, what your color choice is actually meant to encode. Then, we'll translate those purposes into color space and see how each one corresponds to a specific path in the color wheel. After that, I'll introduce professional color palettes that already solve these problems for you. Finally, we'll move to the practical side, how to implement these palettes in Excel and in LaTeX so that you can make an intelligent choice instantly. And if you stay until the end, I'll show you a way to automate this entire process so you can create publication quality figures with robust color choices every single time. Before choosing any colors, you first must answer this question: what is the purpose of color in my figure? Because color is not for decoration. Color is an encoding, and encodings serve for a specific purpose. In scientific figures, the use of color can be reduced to 3 fundamental purposes: sequence, divergence, and contrast. Let's start with sequence. A sequential color map is used when the primary goal is to convey ordered magnitude, from low to high. Typical examples include intensity figures, such as spectrograms, where intensity increases along a scale, population density maps from sparse to dense, probability densities from low to high, and heat maps such as traffic or thermal maps. In all of these cases, the goal is the same: to visually communicate order and magnitude. That is why sequential color maps usually move from light to dark or from low to high intensity. The second category is divergent color maps, which are used when the data varies around a meaningful central value. Classic examples include temperature fluctuations, geometric deviations, gain and loss maps such as net migration and correlation matrices, all centered around 0. The purpose of these figures is not to show order, is to show a specific distance from a central point. That is why the center value is visually neutral, while positive and negative deviations are emphasized using 2 opposing colors. The third category is contrast, sometimes called qualitative color encoding. Contrast is used when the data consists of distinct categories with no intrinsic order. For example, different experimental conditions, different design concepts, cluster assignments, or regions in a map or state diagram. In this category, color is purely used to separate categories, not to imply magnitude, direction, or order. That is why the color scheme is chosen such that the colors are clearly distinguishable from one another. So the first step in selecting a color map is to define your purpose. Are you encoding a sequence? Are you encoding divergence? Or do you want to highlight contrast between different categories? Once you have answered this question, we move on to the next one, which is how to encode this purpose into the color space. And that is what we will cover in the next chapter. How do we translate sequence, divergence, and contrast into color space? Well, for that we need a very simple geometric model of color. A convenient way to think about color is using the color wheel, where color can be described by 3 parameters: Hue, which corresponds to the type of color, is represented here as the angular position. Saturation, which measures how vivid or gray a color is represented as the radius, and lightness, which shows how light or dark a color appears, is controlled by an additional angular parameter. Let's start with sequential color schemes. In a sequential map, the goal is to encode order magnitude from low to high. Geometrically, this corresponds to moving along a single direction in color space, most importantly along lightness. Low values appear light, high values appear dark, while hue and saturation remain largely controlled. This is why good sequential maps feel smooth and ordered. They trace a one-dimensional path through color space. Divergent color schemes are different. Here, the goal is to show deviations around a reference value. In color space, this is represented by two symmetric paths, one defined by a fixed hue on one side, and the other by an opposing hue. Along each path, lightness varies monotonically toward a neutral center. Both sides share the same lightness structure, so equal deviations appear equally strong. This symmetry is what makes divergent maps so effective at highlighting opposites. Finally, consider contrast or qualitative color schemes. Here, there is no ordering and no reference value. The goal is simply to make categories easy to distinguish. In color space, this means selecting discrete points that are well separated in hue and similar in lightness. You can think of this as sampling points that are roughly evenly spaced around the color wheel. Until now, everything sounds clean and mathematical. However, there is a catch. Although you might select a mathematically perfect color scheme, the color scheme might fail perceptually. Consider this divergent color scale. Although it's mathematically balanced, about 10% of humans may struggle to clearly distinguish value trends due to color vision deficiency. Furthermore, some color schemes collapse when printed in grayscale. A classic example is the rainbow color map, which fails to preserve perceptual ordering when converted to black and white. So if you're thinking that color selection is harder than it looks, well, you're absolutely right. That is why, instead of creating our own color palettes, we will rely on professionally designed color palettes, which is what we are going to discuss in the next chapter. We have seen that designing a color scale requires a large number of considerations. Fortunately, some researchers have already spent a huge amount of time and effort to design efficient color palettes. In particular, Cynthia Brewer, Geoffrey Hutcher, and Mark Harrower introduced ColorBrewer in 2003. Their work focused on systematically developing color maps that are perceptually balanced and provide sufficient contrast for different visualization purposes, namely sequential, divergent, and qualitative scales. In 2013, this work was extended into an interactive website. There, you can select the number of data classes you want to visualize and choose sequential, diverging, or qualitative color schemes. Each palette is carefully designed to maintain perceptual balance. Importantly, this website also allows you to test accessibility properties interactively, including color vision deficiencies, grayscale printing, and photocopy safety. Beyond the website, these palettes have also been packed into a LaTeX library, appropriately named ColorBrewer. Within this package, the same color schemes are encoded using standardized names and indices, where each index corresponds to the number of classes being visualized. As you can see, the collection includes all sequential, diverging, and qualitative schemes provided by ColorBrewer. Now that we have identified reliable and well-tested color scales, we're going to put them into practice. To use the ColorBrewer package, you'll first need a working LaTeX environment. I'll walk you through the 4 steps required to apply ColorBrewer palettes to your figures. Step 1 is configuring the document preamble. Right after the document class declaration, you need to include 3 commands. These enable PGFPlots and load the ColorBrewer library. Once this is done, the color schemes become available through your document. Step 2 happens inside the figure environment. Here we define the color palette for the figure. The idea is to encapsulate the palette into a command so that the entire figure can be recolored dynamically. To do this, we include 2 commands. First, one that defines the ColorBrewer scheme, and second, one that defines a PGFPlots color cycle configuration based on that scheme. These definitions can be placed at the beginning of each figure, which allows you to use different color palettes across different figures in the same document. Step 3 takes place inside the axis environment. Here, we simply activate the color cycle we defined earlier by including corresponding PGFPlots setting. This connects the axis to the ColorBrewer palette. Finally, step 4 is adding data series. Each time you add a new series using addPlot plus PGFPlots will automatically select the next color in the palette sequence. This ensures consistent, well-spaced colors without any manual intervention. Alternatively, you may choose a specific color within the palette by adding a minus sign and the letter code to the scheme command, for instance, scheme-C. Let's see this in practice. Here is the chart that I showed in the beginning. The required commands are already defined in the preamble, the color scheme is declared at the figure level, and inside the figure, the ColorBrewer setup is applied. Each data series is added using the plus sign, which advances the color automatically. Now, if I change the scheme name, for example, switching from dark to accent, and recompile, the entire figure updates immediately. As you can see, the new color palette is applied consistently across all series. I hope you find this approach useful. All materials for these examples can be found in the link in the description. Now let's move on to Microsoft Excel. To use the ColorBrewer palettes in Microsoft Excel, we first need to understand how color palettes work here. Excel works with color themes, not individual color maps. For this reason, I've created a separate Excel color theme for each of the 8 qualitative ColorBrewer schemes. These themes are stored as XML files. To install them, simply copy the XML files into the appropriate themes directory. Once this is done, the next time you launch Excel, you'll find these color themes under Page Layout, Colors, Custom. There, you'll see all 8 ColorBrewer qualitative palettes available for selection. Now, let's talk about how to use these palettes for a chart. First, under Page Layout and then Colors, select the ColorBrewer palette you want to use. Next, go to Chart Design, change colors. You will see multiple color options here, but it's crucial that you always select the first palette. All other palettes are Excel-generated variations and do not follow the ColorBrewer philosophy. So for consistency and correctness, always stick to the first default option. If you now go to Chart Design, Format, Shape Fill or Shape Outline, you'll see the theme colors. The first 4 colors, white, black, light blue, and dark blue, are left unchanged across all themes. These are structural colors and are not part of the ColorBrewer palette. The ColorBrewer colors begin with accent 1 through accent 6. Excel allows up to 6 accent colors, and these are precisely where the ColorBrewer palette is applied. These 6 accents are the colors you see automatically assigned to your data series in the layout. To switch to a different ColorBrewer palette, simply go back to the Page Layout, Colors, and select another theme. You can see that the entire chart is updated instantly. I hope that this video has given you a clear, practical understanding of how colors can work for you rather than against you. If you find this video useful, please consider liking it, subscribing to the channel, and sharing this video to other colleagues such that we can save the scientific literature from poorly created scientific diagrams. And if you like to create beautiful publication quality scientific figures, I've created a large collection of charts, scatter plots, line plots, surface plots, and more in LaTeX, all designed using ColorBrewer palettes and following the best publication practices. You'll find access to that collection along with all the material from this video via the link in the description. Thank you for watching, and I'll see you in the next video.